Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Today with problem 129. That rhymed. Some root to leaf numbers, excuse me. It's an interesting problem that's currently being asked by Facebook, Amazon, Bloomberg, and eBay. And I don't think it's too hard to understand, but it's got a couple cool components to it. And so if you haven't read it already, the problem essentially says that we're given a binary tree that contains digits from 0 to 9 only. And each root to leaf path could represent a number. For instance, if we had a path 1, 2, 3, it represents the number 123. We need to find the total sum of all the root to leaf numbers. And we're given as a note that a leaf is a node with no children. I think we know that by now. But just to look at the example more visually, we can see a path here going from 1 to 2, and that goes from the root down to the leaf node. So 1, 2 would represent the number 12. And 1, 3 going down to the right-hand side would represent 13. The solution to this problem, or the output that we want to put out, is 25, which is the sum of 12 and 13. If we look at this example now, which is a bit more involved, we take a look at, we've got 495, 491, and 40 being our three paths. So they represent the numbers 495, 491, and 40 respectively. So I think the problem statement is more or less clear. The solution might not be so obvious immediately, but I think the problem makes sense. So we want to think about a couple of things when we're doing a problem like this. First off, since it's a tree problem, pretty much by default, we're going to have some sort of recursion involved. And since we actually need to go ahead and check every single node, which is most often the case, we're going to have to do a thorough search of the tree. Typically, we can do this in linear time, and this will be the case here as well. And generally, since we're kind of traversing down, I'm starting at the root, I'm going all the way down to the bottom, on these two sides, and even here, I'm kind of looking at this path first, and I'm looking at this path first, and I'll recurse back and look at this one next, and then I'll check this one at a time. That kind of suggests that movement really lends itself nicely to a depth first search instead of a breadth first search. I haven't tried doing a breadth first search. I'm not sure if you could. It might be possible. Let me know down below if you guys have a really clever way of doing it. But if you value your own sanity and mental well-being, you'll go with the depth first search for this question. And so let's think about how we'd approach this. The one way that you could do it, and this could be a bit of almost a hacky or a bootstrap way, and it would take up a bit more space, would be to say, let me do a search of one branch at a time. So I'll start at my root, and I'll check for left and right children. If they exist, maybe I'll go down to my left child first. And what I'll do is I'll keep on searching down my children until I get to our terminal condition. So our terminal condition, remember for recursion we need two things. One is we need the terminal condition, and then the second thing we need is the recursive relationship. Okay? So we have to determine two things. One is, when do I actually stop searching downwards? And the second is, when am I actually calling my recursive calls? Well, the terminal condition in this case, we're really only interested in going down to the leaf node. So I'd argue the way that I've kind of set it up is we want to keep searching. Let's keep searching down a path until we get to the leaf node. So we're gonna set our terminal condition to be a leaf node, right? And typically, what this means, or not even typically, but by definition, what this means is we hit a node that exists. It's not none. However, it does not have a left child nor a right child. So in our terminal condition, we can say if our node has neither a left nor a right child, then in that case we'll do something, then we'll return and we'll say, okay, we've done enough, let's push it back up. But until then, we keep on searching. The recursive relationship then is essentially just going to be, if I'm at a node, let me try to go down both sides of that node. So let me go left if I can, and let me go right if I can. So with this in mind, you might start thinking to yourself, okay, so if I was to go one step at a time, and every step along the way, you can almost think about concatenating one number to another. So in some sense, you can look at the 1 and say, okay, I'll start at a 1, and then I'll keep track of some sort of current path that I'm on. I make it down to my next node, and I see a 2, and I say, okay, I'll concatenate a 2, and then, I'm at the end because we don't have any children, so one of my numbers is 12. And maybe we keep some sort of total where we add these up. The reason I use this word concatenation is because one thing that might be going through your mind is to say, let me let me just keep these as a string. You know, maybe they don't need to be integers. I'll have a string. One is my string, and then I'll append the two. I'll add that on, and I'll keep kind of creating more and more space. What I'll do is I'll then do the same thing, and I'll end up with a string that's 13. I'll convert both these to integers by calling something like int of 12 and 13 and whatever we have those based on, and then add them. This will work, and it's a valid solution, although I suspect that, or first off, I know there's a slightly more clever way to do it, and I suspect that when you're in an interview, you might be asked to produce another way of doing it without using this extra use of strings. To solve this problem, you will need to use O of n space, especially because the recursive calls, actually they add memory onto our call stack. And because there's memory onto our call stack, in a worst case scenario, we can have a tree that looks like a list of just one straight line from top to bottom. And in that case, we'd have a call stack of O of n. So you can't really avoid the space, although using these strings wouldn't actually change the asymptotic analysis, meaning it would still be O of n. The real space will be affected. And again, it's more than likely that the interviewer may ask you to kind of maybe clarify and do a slightly less bootstrappy way. And in that case, you then think to yourself, okay, if I've got a number, actually, I'll do it right here. I'll start with this one because we have a few more digits here. I start with the 4, okay? So I'm saying that on my current path, if everything was to end right here, I have the number 4. Cool. Unfortunately, it doesn't, and we come across this number 9. So then we ask ourselves, okay, how do I get the 9 onto the 4 and do the effect of concatenation, if you will? Well, we know 4, and when we add the 9, needs to become 49. So, okay, isn't it convenient that 49 is just, 4 times 10 plus 9? Like, okay, cool, that gets us to 49. And then what about the 5? Well, we know the 49 is we need to make a 495, and really if you catch my drift here, what's really happening is we need to move this entire number 1 over to the left if you're thinking about kind of your places, like we're moving from the ones place to the tens place, or the tens place to the hundreds place. The way we do that in effect mathematically is we multiply the number we have, the current number, multiply it by 10, add the one we want, and that's going to get us to 495. And so in this case, you can just keep adding these to the total without doing this whole string conversion business. So that's the approach that I'm going to go with. Again, the first one, if you got it, good on you. That will get you to the end. But this might be just a neat little trick to keep in the back pocket in case you find yourself in a situation like this. So apart from that, this is a kind of standard DFS question. So I think we're good with the logic here, and we're in a good position probably to just jump over to the code and see what we can make happen there. So we look at the code here, and the first thing we typically want to do as always is just our standard error checking. And so what I'll say is if not root, then we're going to return none or return root as it is. It really doesn't matter. Or rather, I should say we're outputting the sum. So if we're not given a root, we should actually be outputting 0, okay? So that's going to be our just initial error checking. And I think the way we'll do the solution might actually cover this as well. So we'll see, and this might not be necessary, but I'm putting it here for starters. We're eventually going to need some sort of total, and I'll call that total 0 for now, and I'm going to want to return that total. But in the meantime, I'm going to need to do some sort of a recursive call or a depth first search. And so what I'd like to do then is to say, let me just define some sort of method called depth first search. And now I don't know what I'm going to put in there just yet. Well, I have a rough idea, but what I will need to do is to actually call this this method at some point. So we start with the total of 0. After we error check, of course, we start with the total of 0. We do our depth first search and find whatever we need to. It can, in effect, modify this total, so we can add to it when we need to, and then ultimately we're going to return the total. So what are we actually going to need to pass into here? Well, one thing we're definitely going to need is the node that we're starting at, right? At any given point where we're searching, I'm going to need the root. So what I'll do is I'll call that root and pass it along. The other thing that we said we would need is we would need to keep track of whatever this number is. So, first we have the 1 and then the 12 and so on. And what we can call that is we're starting with 0. So what I'm going to do is I'm going to call it something like cur representing our current number. And as we go, we'll kind of add onto this cur. And as we add onto it, if we eventually hit our terminal condition, we're going to need to add it to the total that we have. So with that in mind, let's think about that terminal condition now. So we said that essentially if we hit a leaf node, we are done. We want to add whatever that leaf node is and after we add the leaf node, we just want to return it. We're done with that branch. So what we can do is this, is we can say if not root.left and not root.right, meaning that it's a leaf node with no children, this means we've hit a leaf node. So if we started with the 1, and now I call the 2. The 2 is a leaf node because it doesn't have any children. I'm going to want to add the 1 onto whatever I'm going to want to add the 2 onto the current value that I had. And so what we said is that current was going to be equal to whatever current was times 10 plus the value of the node that we're on, so plus root.val. So, and I know I haven't written the code out here for this yet, and we're going to want to return after this, but imagine we're walking through this scenario. I find the 1, and what I'll do is I'm going to update my current to house this 1. And the way I do that will actually be through the exact same formula. I'll say that current is equal to current times 10 plus root value. We're starting with 0, so I'm starting with no current value. Sorry guys, my phone bugged out, so it's gonna be all choppy here. But I was basically saying that what we want to do is we're starting with the current value of 0. We multiply by 10, which leaves us with 0, and now we add the 1. Our current value is now 1. From this 1, I want to check if I have left or right children, and if I do, I want to add those values to my children. I want to check if root.left, I'm gonna call left, and if root.right, I also want to make a call to the right? My call to the left is going to be simple. I'm just going to call DFS, and I'm going to call it on root.left and current, which I've already updated here. And same thing for the right. I'm going to call it on root.right with cur right there. Now, if I was to continue with this example here, our current value went from 0 to 1 when we started with our original root. I'm now calling root.left, and there's one thing I forgot here. I'm now calling root.left. Once I call root.left, we're going to jump into this left node, 2. Since 2 has no children, we need to update. So cur is going to go from 1 to 1 times 10, which is 10, plus root.val, which is 2. Current is now at 12. Since we are at the end, we've hit a leaf node. 12 is the sum of this path. I now need to add the sum of this path to the total. So I'm going to say total plus equals, cur, right? So I didn't add that earlier, so my apologies. We need to update this total value when we hit the end of a path. What I will say as well is that in Python, likely you will need to, just because of the scope, so this is defined outside of the scope of this function, you may need to use the keyword non-local just to tell the program to look outside of the scope of that, the DFS function. So we update the current, we add the current to the total, and we return. We're done here. So this node 2, which we had now, is effectively popped off of the call stack. Okay, it's off of the call stack, and what's happening is we're now going to take this next step through the code and jump into the node 3. So we're looking at the node of value 3 now. It also doesn't have any children. Our cur, since we took a step back, we popped off that 12, it's still at 1. The cur is at 1. 1 times 10 is 10, plus root.value 3 is 13. Total is increased by 13. We used to have 12, now it's 13. The total is 25. And we return. We're done here. We popped it. Once we're done here, we've jumped out here. We've completed all of our searches. Total will be 13. So we've completed this call, and we're going to return that total is 25, not 13. It's 12 plus 13, which gives us 25. So we return the total of 25, and if I didn't make any mistakes, that should be it. I'm just going to submit this and make sure it works all right. And there we go. So overall, it's a relatively standard DFS problem with a couple of small tweaks. And if this is a problem you're not fully comfortable with, or maybe you're not fully comfortable with trees, I think this is a good quasi entry-level problem for you to just get your hands dirty with a bit. And doing more problems like these will definitely help you get there in no time. All right. So I hope you guys found this video helpful. The whole good stuff about like, share, subscribe. You know the drill. And let me know down below if you have any questions on either this problem or any other problems you want me to do. And in that case, I'll see you guys next time. Peace.